class I introduced the picture through which we interpret the observed large scale structures, and the picture is that we have a statistical process which produces the fluctuations that we see, the observed fluctuations that we see, and the observed fluctuations that we see is interpreted as being one realization of this statistical process. So, the process being statistical, we cannot predict the outcome of the process. We can only predict the mean values. I had given you the example of throwing the dice. I cannot, if I have a fair dice for example, I cannot predict what the outcome will be when I throw the dice, but I can predict that I will get 1 to 6, some number between 1 to 6 with equal probability 1/6. I can also predict the expected outcome, the mean outcome. If I repeat the experiment many times, I can predict that I will get a value 3.5. Similarly, whatever statistical process produces these fluctuations in the universe, the large scale structures, I cannot predict what one realization is going to look like, but I can predict the ensemble average. If I were to have a large number of all possible realizations, and then if I were to average some quantity over this, I can predict what the average would be, and such an average is referred to as the ensemble average. This was the first thing. The second thing that I had told you is, it is assumed that the statistical process is homogeneous and isotropic, and this is referred to as statistical homogeneity and isotropy. So, this shows you pictures of different realizations, cartoon pictures, schematic diagram representing different realizations of the fluctuations that we see in the universe. And if I take a point x, some fixed point x, and ask the question, what is the ensemble average of the density contrast at that value, at that position x, then from statistical homogeneity we can say that this has to be equal to 0, because if this had a particular value, then the value would be specific to the position and it would break homogeneity. Okay. So, the ensemble average of delta x of the density contrast has to be 0. The next thing, the higher order quantity that we looked at was the 2-point correlation function, which is the product, the ensemble average of the product of the density contrast at two different points, which is why it is called the 2-point correlation function. And the information in this is that is the density fluctuation at this point and this point, these 2 points x1 and x2, are the density fluctuations at these 2 points correlated? If they are correlated, then this will have a positive value. If they are uncorrelated, this will be 0. If they are anti-correlated, it will have a negative value. And it is defined as follows: you take the density at the density contrast at this point, the density contrast at this point, you multiply them and then take the ensemble average. This is xi x1 x2, it is a function of these two positions. Then from statistical homogeneity, I had told you that the xi can depend only on the difference, the vector joining these 2 points. It then becomes statistically homogeneous, and from isotropy it can only depend on the magnitude of the separation. So, finally, this xi depends only on the magnitude of the separation between these 2 points. In the linear regime, when xi is extremely small, if the correlation is much smaller than 1, we can apply linear theory of density perturbations. Linear theory is valid, and then we know that xi with time it will scale like this, it will just get multiplied by the growing mode squared. Okay, so, if I On sufficiently large scales, we know that the fluctuations grow on scales larger than the Jeans length scale. So, on sufficiently large scales, if I start off with a certain value of xi, then the amplitude, that correlation is going to grow proportional to the growing mode squared. Okay. So, if I had a small fluctuation clustering pattern to start with, that clustering pattern is going to grow, and we can quantify it using the 2-point correlation function. Now, the question arises, how can we observationally determine the 2-point correlation function? To observationally determine the 2-point correlation function the way it has been defined, I need to have different realizations of the fluctuations, but we only have one realization, one observed universe. I do not have different realizations of the same fluctuation. Okay. So, the way you observationally determine this, let me explain that. So, this is the observed universe, let us say, the part of the universe which I can observe. So, my observations usually never span the entire observable universe, they are usually restricted to a part of the observable universe. Whatever it is, this is the part of the universe which is amenable to, accessible to me now. So, this is my observed universe, observation. So, this is the volume of my observation. Okay. In principle, if I want to measure the 2-point correlation function between 2 points, let us say this point is x1 and this point is x2, I should take different realizations of the density fluctuation at the same position and multiply the density contrast and then take the average across all these realizations. It is not possible, but we know, we believe that the 2-point correlation function depends only on the separation x between these 2 points. The statistical process is homogeneous and isotropic, it only depends on the separation. So, what is done is that this ensemble average is not available to us, but so we cannot do this ensemble average. The average that is actually accessible to us is that we can do the average over different such separations x. So, I can consider this, then I can consider 2 points same distance at the same distance x. Okay. So, what is done is that you consider all pairs of points at a separation x, determine the density fluctuation, the density contrast at these 2 points, and then you average over all such different points, pairs of points. Okay. So, you replace the ensemble average you cannot do this actually by a volume average. You average over the region, all such pairs of points that you can place inside this region, you average over that. Okay. So, this is actually replaced in reality by a volume average. Under the assumption that the signal is homogeneous and isotropic. Okay. So, this and this give us 2 independent, it is assumed that these 2 pairs of points gives us one realization, one estimate of the 2-point correlation function. This gives us a different estimate, this gives us another one. You take all such possible pairs and you then average over it. Okay. I hope this is clear. This is how the 2-point correlation function or all other such statistics is actually evaluated. Okay. Now, one straightforward outcome of this is as follows, which let us ask the question. So, say let me draw the same picture first. This is the picture. First, let us consider the situation where I determine the 2-point correlation function at a small separation x, x1. Now, it is obvious that there are many such independent pairs which I can place inside this. Okay. On the contrary, if I try to determine the 2-point correlation function at a large separation x2, there are very few such independent pairs of points that I can place inside this. Okay. So, the error, this is going to have a larger error, or rather more errors, because I am estimating the mean from only a few set of such values. I will get a poor estimate of the mean. I will get a much better estimate of the mean for these small separations. Okay. This is called, so this will introduce, so I will have inherent to my observation, there will be some errors to this, to the 2-point correlation function at large separations. These errors will be much smaller for 2-point correlation function at small separations. This is referred to as the cosmic variance, okay, or sample variance. Now, the 2-point correlation function has been observationally determined, the 2-point correlation function, and it is found that xi r is quite well represented by a formula like this. Xi r is r by r naught to the power of minus gamma, with this index gamma with the value around 1.8 and r naught a value around 5 or 6 megapar, somewhere in the range 5 to 6 MPC. I am giving you rough values. Okay. Now, such a power law 2-point correlation function indicates that there is some scale invariant, the perturbations are scale invariant. Okay. The fluctuations, the correlations are scale invariant. So, fractals have such power law 2-point correlation function. So, this the 2-point correlation function in the, this is for galaxies. Okay. If you take galaxies, this is the galaxy for galaxies. Okay. So, the galaxy distribution shows some kind of a scale invariant fractal behavior on small scales. This is only valid on small scales. So, this is roughly valid on scales less than 20 MPC. Okay. And such a behavior is referred to as a scale invariant behavior. It is a property of fractals. So, this is what the 2-point correlation function looks like on small scales. These are not the scales. You see the role of this r naught, this is the correlation length. R naught is called the correlation length. The 2-point correlation function is more than 1 on length scales smaller than the correlation length. Okay. So, it sends the length scale where the 2-point correlation function crosses unity, and once you are in a regime where it crosses unity, you are no longer in the linear regime. So, these are the this is the region where it is strongly clustered. Okay. In the last class, I had also introduced the 3-point correlation function zeta. Okay. Now, it is found that on small scale, so I am talking about small scales, scales less than few of the order of few megaparsecs. On small scales is zeta x1, it is a function of 3 positions x2, x3. It is found empirically that this is quite well represented by a formula of this type. Plus other combinations. So, this is xi 1 3 1 2 1 3, and then I can have other terms xi x 2 1 xi x 2 3 plus xi x 3 1 xi x 3 2, okay, where q is a number of order unity. So, it is found that the 3-point correlation function is related to the two products of 2-point correlation function like this. This is empirical. Okay. This is called the hierarchical form. So, this is empirical finding. So, I have now given you some idea of the observational situation very briefly regarding the 2-point correlation function and the 3-point correlation function. These are the correlation function as determined from the galaxy distribution. So, you take the galaxy distribution and find the mean value, then take the actual density, subtract it and divide by the mean, you get the density contrast. Once you have the density contrast, you can find the 2-point correlation function, 3-point correlation function. Okay. Next, in the last class, I had also gone over to Fourier space. Okay. Fourier space has certain advantages. So, the same density contrast field can also be represented in terms of Fourier modes. So, this is I am representing it in terms of a Fourier integral, and there are these Fourier modes with Fourier, each mode has a wave number k, co-moving wave number, and it has an amplitude delta k. Right. So, all the entire density fluctuation field can also be equivalently represented in terms of delta k. Instead of representing it in terms of delta x, I can equivalently represent it in terms of the Fourier amplitudes of different modes. This, remember, is a complex number. Okay. Having done that, now we would like to characterize the statistics just like the 2-point correlation function. What we can do is take the amplitude of a particular co-moving of a particular mode, take the amplitude of a different mode, multiply them, take the complex conjugate of 1, multiply these two, then take an ensemble average. So, determine these numbers for different realizations and then take an ensemble average. Okay. This is very useful in characterizing the statistical properties of the density fluctuation. Okay. Now, let us see how this is related to this delta x. So, this relation needs to be inverted. Inverting this relation is quite straightforward, or yeah. Let me write down the inverse relation first. The inverse relation is delta k is equal to d cube x So, it is straightforward to check that the inverse relation relating delta k to this delta x is given is this. Okay, this is delta x. Okay, this and this are the inverse of each other. Now, this delta k then can be written as now let me actually work the other way around. We are interested in evaluating this. Let me work the other way around. Let me write the 2-point correlation function in terms of this. So, This we know is the 2-point correlation function xi at A. This is xi at A, because A is the separation between these 2 points. Okay. This we know is xi of A, and we can write this as each of these we can express in Fourier space. So, in Fourier space, the first term is going to be d cube k by 2 pi cube delta k e to the power I k dot x. So, all that I have done is I have expressed the first density contrast delta x like this. Okay. Let me express the second one now. The second one can be written as d cube k prime 2 pi cube. Now, I can always take the complex conjugate of this entire equation. If I take the complex conjugate of this entire equation, then delta, the density contrast, we know is a real quantity, it does not get affected. I will have delta star over here, I will have a minus sign over here. Okay. So, I can equivalently write that delta at density contrast at x plus a as del star k prime e to the power minus I k prime dot x plus a, and I have the ensemble average of this whole product. Now, here the ensemble average, when I go from one realization to another, the only thing that changes is this delta k. All these factors are not different for each realization to the other. The only thing that changes from realization to realization is the delta k. Okay. So, this can actually be written as d cube k prime 2 pi cube then I have e to the power I k dot x e to the power minus I k prime dot x plus a, and I have this ensemble average delta k delta star k prime, which we were interested in. Right. Now, we have done some algebra. Now, we want to make some sense out of it. To do this, let me now do one more thing. We have to use the statistical homogeneity. So, what do we mean by that? If instead of considering the product of these two density contrasts, if I had shifted each of them, so if I had considered x plus y delta x plus y plus a, I have shifted the origin of, I have shifted. So, I am considering a situation where I have shifted both the points by a vector y. This ensemble average is still going to be xi of a, this is not going to change. If the density fluctuation field is statistically homogeneous and isotropic, this will still be a function of xi of a, it will only be a function of the vector a, of the mod, the length a. Okay, I am writing it as the vector, but it will only be a function of. So, this again, let me now straight away replace x with x plus y in each of these, right. The same thing will go through. So, this will be d cube k prime 2 pi cube and here I have e to the power I k dot x plus y and here I have e to the power minus I k prime dot x plus y plus a, these three vectors. And here I have the ensemble average of delta k del star k prime. Okay. So, what we have done is we have evaluated the same thing, shifting my origin by a vector y essentially, and from statistical, or I have shifted these two pair of points by a distance y. If the density fluctuation, the statistical process is homogeneous and isotropic, this will not change. Okay. So, this should give me the same thing. Now, here I can isolate the part which depends on y. Let me do that. Okay. So, this we can write as d cube k prime by 2 pi cube and here I have e to the power I k dot x, I am not putting the vector sign, e to the power minus I k prime dot x plus a, these are all vectors, I am not putting the minus sign. Let me isolate the term involving y, e to the power I k minus k prime dot y, these are all vectors, bear in mind, into delta k del star k prime. This is what I have. Now, we would like this to be exactly equal to this, right, because if the whole thing is statistically homogeneous and isotropic, finally it should not depend on y. So, we would like this and this to be the same. Now, question is, under what condition then is this thing finally going to be independent of y? Okay. And the condition is quite obvious. The condition is that this integration is going to be independent of y only if this term over here is 0 whenever k and k prime are different. It is non-zero only when k and k prime are the same. If k and k prime are the same, then this term does not contribute. Okay. So, statistical homogeneity for isotropy has not come into the picture as yet. Statistical homogeneity implies that the ensemble average of the product delta k and delta star k prime, this should be equal to the Dirac delta function. These are continuous variables. So, we use the Dirac delta function, delta Dirac, 3-dimensional Dirac delta function k minus k prime. So, this has a value, non-zero value only when k and k prime are the same. 3-dimensional because k's are 3-dimensional vectors, kx, ky, kz, all three of them should match. Okay. And it is convention to write it like this, 2 pi cube into p of k. Okay. This could be, so these two will have a value only when k and k prime are the same, and the value then is this into this, otherwise it is 0. Okay. So, if I use this over here, then one of these 2 pi cubes is gone. I have a Dirac delta function k minus k prime. So, when I do the k prime integral, essentially k gets replaced by k prime gets replaced by k. Okay. So, I can straight away write down that this will be equal to if k and k prime are the same, then here e to the power I k x minus I k x, they will cancel out, and what I will be left with is e to the power minus I k dot a. So, from homogeneity I have this, and from statistical isotropy I can say that this should not depend on the vector, it should be just a function of the magnitude. Okay. So, this quantity P of k is what we refer to as the power spectrum. And it is quite clear that this is xi of a, that the power spectrum is the Fourier transform of the 2-point correlation function xi a. Right. So, it is the Fourier transform of the 2-point correlation function. This is the Fourier transform of xi x, if you wish. Okay. So, the power spectrum is the Fourier transform of the 2-point correlation function, and the power spectrum you can think of it as being the so if I decompose the density contrast field into these Fourier modes, the power spectrum is essentially the square of the amplitude of the Fourier mode at each k. Okay. The power spectrum, it is clear also from this definition here, the power spectrum involves 2 deltas and it has a value only when the k's are same. So, from statistical homogeneity we see that the amplitude of different wave numbers of different modes are uncorrelated, and when they are the same you get the power spectrum. Okay. The power spectrum essentially is a function of p, it is p as a function of the co-moving wave number, and it tells us, it quantifies the amplitude of the fluctuation at a co-moving wave number k. Okay. It quantifies the amplitude of the fluctuation at a co-moving wave number k, which is the inverse wavelength. So, and it is the Fourier transform of the 2-point correlation function. So, the power spectrum is very useful in quantifying these large scale structures that we see. Okay, the power spectrum is very useful in quantifying the large scale structures that we see, and with time in the matter dominated era, or after the radiation dominated era, this scales as d square t, same just like the 2-point correlation function. Okay. So, on large scales it is most convenient and useful to represent the statistical properties of the density fluctuation, observed density fluctuation through the power spectrum. Let me show you here a picture of the power spectrum, of the dark matter power spectrum, as it has been determined from a variety of observations. Okay. So, this picture essentially summarizes an entire set of a large variety of observations which together determine the power spectrum. Okay. So, there are observations, I shall not have the opportunity to go into the details of any of these observations, but let me briefly mention them. So, on these are the small scales, the larger the wave number, the smaller the length scale, right, because I have told you that the wave number and the length scale are inversely related. K is 2 pi by lambda. We all know this, okay, and K of order 1 implies lambda of order 6 MPC, right, 2 pi. So, okay, here it actually shows you both. This diagram actually shows you both. You have the wavelength in wave number in the lower axis, you have the wave number in the lower axis, you have the wavelength which is 2 pi by lambda in the upper part, right. So, you can see that 1 corresponds to around 6, 2 pi, little more than 6, okay. And scales to the right of this, so to the right of this are non-linear, we have already seen that, right, the 2-point correlation function exceeds unity. So, the scales over here are non-linear, and these scales are, the scales over here are probed by something called the Lyman alpha forest, and the scales here at these length scales are also probed by the galaxy distribution, but that has not been shown in this picture, okay. So, the galaxy distribution also probes the power spectrum, not the dark matter. So, this is the dark matter power spectrum. What you can measure from galaxy distributions are the galaxy power spectrum. I have already introduced the concept of bias, and they will be related through a bias parameter squared, okay. Now, here they are, okay. Now, this part of the power spectrum shown over, the one shown over here, is actually probed by Lyman alpha forest. These are features in the intergalactic medium, okay, the region, the material in between the galaxies over there. The black, okay, it also shows you the galaxy survey. So, the region probed by the galaxy survey are the black, the points from the, sorry, I had mistakenly said it is not shown here. The black points over here are the powers, are the results from the Sloan digital redshift survey. I have shown you pictures of the Sloan digital redshift survey earlier on, right. So, if you analyze the clustering pattern of galaxies over there, then you can determine the power. So, what you do is you have the observation, this is a region of space which has been surveyed, you have the galaxy distribution, you can get the delta x from this, and then you can decompose it into Fourier modes and determine the power spectrum, okay. So, this has been done using the Sloan digital sky survey, and this is what the power spectrum looks like. The black points over here show you what the power spectrum looks like. There is no detection at these 2 points, these are upper limits. So, the value will be, actual value somewhere below this, okay. Then you have cluster abundances. I have told you about clusters of galaxies, the fact that they appear, there are regions where you find large density of galaxies, these are called clusters of galaxies. Now, the observed abundance of clusters, that is the number of clusters you have per unit volume, this is closely related to the dark matter power spectrum, and the observed abundance of clusters imposes constraints on the power spectrum. The power spectrum then must lie. So, this is the length scale corresponding to a cluster of galaxies, this is the length scale, okay. A perturbation of this length scale actually grows to form a cluster of galaxies, and if the perturbation is too small, you do not have sufficient number of clusters. If the perturbation is too large, you have too many clusters. So, this is constrained by the cluster abundance, okay. Then there is this weak lensing, this is lensing by the dark matter fluctuations, and this is a probe of the dark matter power spectrum. It probes this part of, these are all in the linear regime, nearly in the linear regime, and observations of the cosmic microwave background radiation, anisotropies in the cosmic microwave background radiation. They probe the large scales, they probe the largest scales possible, and these observations are from there. Now, this is the black line is the currently popular theoretical model for the dark matter power spectrum. Okay, it is the currently accepted theoretical model for the dark matter power spectrum. Let me very briefly explain to you how this theoretical model works. Okay. Let me explain to you the ingredients of this theoretical model. It is a very simple model. So, the ingredients are as follows. So, in this model at some very early time t initial, the power spectrum P of k is of this form. Now, I will not go into the reason why it is of this form, but okay, there are reasons, I shall not go into that, but at some very early epoch the power spectrum looks like this. Okay. And at that epoch, now let me draw a diagram over here. This diagram, you have eta, this is C eta, and this is the comoving length scale x. Okay. This is the Big Bang, when the universe started. Now, let me draw the causally size of the causally connected region. That is a 45-degree line over here, right. We have learned this already. This is the propagation of light. At the Big Bang, if a signal starts propagating from here, after some conformal time eta, it would have reached this distance. So, a length scale larger than this is not causally connected at this instant of time. Okay. Now, let me consider a fluctuation on this length scale hypothetically. A fluctuation on this length scale. This fluctuation is not causally connected all the way up to this time instant. Right. Now, you may ask the question, how was such a fluctuation produced? We will not go into that issue. Okay. So, let us consider a fluctuation that is this big, comoving length scale. So, from the Big Bang till this epoch, this fluctuation was not causally connected. Okay. It is only at this epoch that the fluctuation becomes causally connected. Now, we have studied the gene's instability. In the gene's instability, we have learned that it is the pressure gradient which prevents fluctuations from growing, right. Now, the signal propagates at the speed of sound. Now, early in the universe was dominated by radiation, and we had this radiation, there was some small amount of baryons, electrons. So, this radiation was the fluid that filled the entire universe. For radiation, we know that the pressure is 1/3 rho c square. This is all radiation dominated. So, the pressure is 1/3 rho c square. The sound speed we know is del p del rho, which is 1/3 c square. Sorry, the square root of this is the sound speed. So, Cs is the speed of light divided by √3, because the fluid itself is a photon fluid, right, but they are not moving in, we are interested in random motions of the photon. So, that is actually one factor of √3 smaller, because it can move in all directions. Okay. So, the sound speed in that fluid, in that radiation fluid, is 1/3 the speed of light. Now, the genes, the pressure gradient becomes operational only when the information crosses this distance. Before that information crosses this distance, the perturbation collapses. Okay, it is growing. the moment the information that there is a perturbation crosses this distance, the pressure gradient will act to stop the growth. Okay. So, let me, so this perturbation which was now not causally connected, the amplitude would have grown by gravitational instability. The moment the information that there is a perturbation on this length scale, this becomes causally connected, it stops growing. Okay, because the sound speed is roughly the speed of light. Okay, so the pressure gradient would have built up only at this instant of time, not before this. So the perturbation here stops growing. Let us take a larger perturbation. Let us take this perturbation. This perturbation will stop growing at this instant of time, much later. And this, so this will continue. Now there is an epoch of matter radiation equality, C eta equality. This is the epoch of matter radiation equality. We have estimated the redshift, it is of the order of 10 to the power 5. Once the universe becomes matter dominated, the Jeans length scale, the sound speed falls drastically, right. Before the universe is matter dominated, the sound speed is approximately the speed of light. After the universe becomes matter dominated, the radiation no longer plays a role. Okay. So the sound speed actually drops drastically, and this, the Jeans length becomes, to the dark matter, it is a dark matter dominated universe. In the dark matter there is no pressure. Okay, so the sound speed effectively falls, this whole process is no longer operational. Once the universe becomes dark matter dominated, it has no pressure, all perturbations start to grow. Okay. So with this background, let me now explain to you how this power spectrum, which originally was like this, I will not go into the mathematics, but it is not very difficult. So my power spectrum was originally like this. As it evolves, what happens? This length scale enters the horizon at a certain time. This is the horizon. Once it enters the horizon, it stops to grow. Okay, so this stops to grow. This is a smaller length scale, it stops growing earlier. This perturbation on this length scale stops growing earlier because it enters the horizon earlier. This is a larger length scale. So let us say this larger length scale, it enters the horizon later. So it stops growing later. So in between, this power spectrum would have grown. This value would have remained like this value would have grown. So in between here it would have become something like this. This stops growing later. Now let us take this. This will enter the horizon later. It's a larger length scale. So it will stop growing later. So it will become like this. Now this mode, let us say, enters the horizon after the universe becomes matter dominated. It does not stop growing at all. All these modes which enter the horizon after the universe becomes matter dominated, they do not experience this period of stopping. So they will remain like this. So the power spectrum will look like this. The present power spectrum will look like this. This is the mode that entered the horizon at the epoch of matter radiation equality. That is the last mode. That is the last mode that experienced this. Once the universe becomes matter dominated, all modes, the Jeans length scale, the sound speed falls drastically. It is no longer comparable to the speed of light. Okay. The dark matter is essentially pressureless. Pressure gradients do not act. Okay, that is the dominant component. Here the dominant component is the radiation, whose pressure is determined is 1/3 rho c square. Here it becomes dark matter dominated. The random velocities of these dark matter particles are extremely small, quite small. They do not have pressure. Okay. So, once you enter the dark matter dominated era, the entire perturbation starts to grow, all perturbation. So, after, so let me draw the picture on a different scale. So, this is my initial perturbation power spectrum. It with time it becomes like this, then it would have become something like this, and once it becomes matter dominated, the universe becomes matter dominated. The same thing, all length scales, they grow in exactly the same way, it just gets multiplied. In the matter dominated universe, I have told you that the shape does not change, it just gets multiplied by d square. Okay. So, this change in the shape occurs only when it is radiation dominated, and the mode where you have this, the bend in the power spectrum, this is k equality, it is of the order of 2 pi by C eta equality, and C eta equality you can determine very easily. Let me explain to you very briefly how to determine C eta equality. So, we know that dA dt 1 by A, that is the Hubble parameter, is equal to C is equal to H naught, and here I have omega matter naught A minus 3 plus omega radiation naught A minus 4, all the relativistic particles, this to the power half. This equation can also be written as dA d eta, d eta is dt by A, so I have to multiply it by A square, so we can integrate this, it is quite straightforward, right, and I have given you the values of these two quantities, and eta equality is the value where these two numbers become the same. So, A equality is equal to when these two terms will become same at A equality, and eta equality is the corresponding value of eta, where A acquires this value. Okay, that is straightforward to calculate from this, and K equality, as I have told you, is the mode that enters the horizon. The size of the horizon is C eta. So, the mode that enters the horizon, K equality, is 2 pi by C eta equality. So, this I leave for you to work out, and you can check that it is quite straightforward to check that it corresponds to this peak of the power spectrum. Okay, somewhere over there. So, this is a very sensitive probe of the omega matter and omega relativistic particle ratio that decides the peak of the power spectrum. Okay, this bend, and this part, these had entered the crossed the horizon before in the radiation dominated era, these cross the horizon in the matter dominated era, these scales are just crossing the horizon. Okay, so let me stop here for today. So, you please work out this K eta, okay, K equality, it is not very difficult, straightforward. I have given you the values of omega matter and omega relativistic.